Hello, myself Shubhashish Shah, Assistant Professor of Mathematics of Greater Kolkata College of Engineering and Management, GIS School. In this video, I will discuss about the remaining tests for convergence of infinite series. In my previous video, I have already discussed the definition of infinite series and some test for convergence of infinite series. So there are some remaining tests I will discuss now. The name of this subject is Mathematics 3, subject code is BSC301, and this subject is for the students of Computer Science, Engineering and Information Technology. The module number is 1. So let's start the discussion. So today's first test I will tell you, that is RABS test. RABS test. So the statement of this test is if summation un be a series of positive terms such that limit n tends to infinity n into un by un plus 1 minus 1 equal to L, which is a finite real number, then number 1, summation un converges if L greater than 1. Number 2, summation un diverges if L less than 1. And number 3, the test fails, that is we can't conclude anything if L equal to 1. We can't conclude anything from this test, so we have to apply another test for that series. Okay, so now I will take an example of RABS test. Example is, let the series is summation n equal to 1 to infinity 3 into 6 into 9 into ... 3n by 7 into 10 into 13 into 3n plus 4. So this is the series, and we have to check the convergence and divergence of this series. So now I will apply RABS test. Okay, I should tell you here that there is no such theorem to by which you can understand, just by seeing the nth term or the series, you can understand which test has to be applied to determine the convergence or divergence of that series. So you can apply arbitrarily any test. If that test fails, then you have to apply another test like this. Okay, so here for I am taking the example for RABS test, so I am applying RABS test directly. Okay, so we have to find this limit. Okay, for that I am removing this. So we have to find limit n tends to infinity n into un by un plus 1 minus 1. Now here un equal to this 3 into 6 into 9 into up to 3n, and 7 into 10 into 13 up to 3n plus 4. This is un, and then un plus 1. Okay, I write here un plus 1 will be 3 into 6 into 9 into 3n into 3n plus 3. That is, we are putting n plus 1 in place of n, and then by 7 into 10 into 13 into 3n plus 4 into 3n plus 3 plus 4, that is 3n plus 7. This will be un plus 1. Okay, now I'll put the values of un and un plus 1 here. Okay, so this will be limit n tends to infinity n into, now un is divided by un plus 1. That is, if we I am not writing the whole terms here, just I write by simplifying. If we divide un by un plus 1, now see that this part will be cancelled out. Okay, so the remaining part will be 3n plus 7 by 3n plus 3 minus 1. So this is after simplifying. Okay, this is the term. Now limit n tends to infinity, I'll subtract this 3n plus 3, and this will be 3n plus 7 minus 3n minus 3, that is 4. So 4n by 3n plus 3. So this will be equal to limit n tends to infinity. We are dividing by n in the numerator as well as in the denominator. So it will be 4 by 3 plus 3 by n. And since n is tending to infinity, this will be 0. So the answer is 4 by 3. And 4 by 3 is greater than 1. Now according to the statement of Rabb's test, if the limit is a finite real number, 4 by 3 is a finite real number, and if it is greater than 1, then the series is convergent. So here we can see that the limit is a finite real number and greater than 1. So this series will be convergent according to Rabb's test. So this was the example for Rabb's test. Now I will discuss next test, Leibniz test. And this test is for, till now I have discussed all the tests for series of positive terms, but this Leibniz test is for the series of alternating terms. That series is called alternating series. So the name is Leibniz test. Okay, so if an alternating series means one term is positive, that is u1 minus u2 plus u3 minus u4, like this, plus minus plus minus. If an alternating series u1 minus u2 plus u3 minus u4 plus dot dot dot, like this, and un greater than 0 for all n, okay, be such that number 1, un plus 1 is less than equal to un, okay, and number 2, limit n tends to infinity un equal to 0, then the series is convergent. So for convergence of the series, these two conditions has to be satisfied. Okay, so now I will take an example of Leibniz test. Let us take this example, number 1, 1 minus half plus 1 by 3 minus 1 by 4 minus plus dot dot dot. Now see that this is an alternating series, okay, and here un will be 1 by n, the nth term is 1 by n. Now first condition we have to check this. So if un is 1 by n, then un plus 1 is 1 by n plus 1. Now we are subtracting un from un plus 1, that is 1 by n plus 1 minus 1 by n. We are doing this to check the first condition. If it is negative, then we can say that un plus 1 is less than equal to un. So obviously it is clear that it will be negative, because 1 by n plus 1 is less than equal to 1 by n, though we have to show it. Okay, so it will be n into n plus 1, and the numerator will be n minus 1, that is equal to minus 1 by n into n plus 1, which is less than 0. So since this is less than 0, then we can say that un plus 1 is less than equal to un. So the first condition is satisfied. Now the second condition, that is limit n tends to infinity un, and here un is 1 by n, and limit n tends to infinity 1 by n is 0. So the second condition is also satisfied. So since 1 and 2 both are satisfied, then we can say that the alternating series, given alternating series is convergent. Okay. So for being convergent, both the conditions have to be satisfied. Okay. So next, this was all the tests. From the first, I have discussed P series, comparison test, Cauchy's root test, D'Alembert's test, and Rabb's test and Leibniz test. Okay, so this was the test included in your syllabus, and now I will give you some definitions, and then I will solve some problems, generalized problems for you. Okay, so now first we have to know some terms. So the first is absolute convergence. Absolute convergence. Okay, so what is absolute convergence? A series is said to be absolutely convergent if summation of mod un is convergent. Okay, that is after taking the modulus of all the terms, the series is convergent, then the series is said to be absolutely convergent. And the next point is conditional convergence. Conditional convergence. So what is conditional convergence? A series which is convergent but not absolutely convergent, is said to be conditional convergent. Okay, so now I will give you some examples of absolute convergence and conditional convergence. So example number 1, we take that 1 minus 1 by 2 cube plus 1 by 3 cube minus 1 by 4 cube plus ... Okay, so here you can see that this is an alternating series. So if we apply, we have to apply Leibniz test for alternating series. We have to for checking the convergence of that series, we have to apply the Leibniz test. Okay, so by Leibniz test, first you write un will be 1 by 2 to the power okay, so here this is a P series. Here we can see that here this is a P series where if we take the modulus of all the terms, then it will be 1 plus 1 by 2 to the power 3 plus 1 by 3 to the power 3 plus ... That is summation of modulus of un will be summation of 1 by n to the power p, where p equal to 3. Okay, so we know that in a P series, if p is greater than 1, then the series is convergent. So after taking modulus, that is summation of mod un, so this will be all sign will be positive plus, so this will be convergent by P series. Okay, now if we check the convergence of this series without taking modulus, we are checking the convergence of this series. This is an alternating series, so we have to apply Leibniz test, and un will be 1 by n to the power 3, 1 by n to the power 3, and according to Leibniz test we have to first check that first condition is un plus 1 should be less than equal to un. So un plus 1 is 1 by n plus 1 whole cube. So obviously un plus 1 is less than equal to un. So first condition is satisfied, and if we calculate limit n tends to infinity un, that is limit n tends to infinity 1 by n cube, this will be 0. So the second condition is also satisfied. So we can see that according to Leibniz test, this alternating series is also convergent. Okay, so what we see, we observe that the given alternating series is convergent, as well as after taking the modulus of all the terms, that is summation of mod un becomes a p series where p is equal to 3 and the series is convergent. So summation un and summation of mod un both are convergent. So we can say that this series is absolutely convergent. Okay, so this was the definition of absolutely convergent. If the series is summation of mod un is convergent. Okay, now I will take an example for conditional convergent. Let us take 1 minus half plus 1 by 3 minus 1 by 4 plus dot dot dot. Now when we are discussing Leibniz test, I have already checked the convergence of this series. So applying Leibniz test, we saw that this series is convergent. That is according to Leibniz test, this alternating series. Now to check that this series is absolutely convergent or not, we have to check the convergence of summation of mod un, that is 1 plus half plus 1 by 3 plus 1 by 4, this series, and this is a p series. This is a p series where p equal to 1, and since p equal to 1, we know that if p is less than equal to 1 in p series, then the series is divergent. So we see that the given alternating series is convergent but not absolutely convergent. After taking modulus, it is not convergent, it becomes divergent. So this series will be called conditional convergence, because the definition was convergent but not absolutely convergent. So this series is convergent but not absolutely convergent. So we can say that this series is conditional convergent. Okay, so this was an example of conditional convergent. Now all the tests and definitions included in your syllabus I have discussed. Now I'll solve some general problem of series. Okay, so the first problem is 6 by 1 into 3 into 5 plus 8 by 3 into 5 into 7 plus 10 by 5 into 7 into 9 plus dot dot dot. So you have to check the convergence of this infinite series. So this given infinite series can be written in the form n equal to 1 to infinity un, where un is equal to 2n plus 4, that is 6, 8, 10. These numbers are the general, the nth term of this series will be 2n plus 4, and in the denominator 1, 1, 3, 5, the first numbers of these products in this series. The nth term of the series will be 2n minus 1, and then 2 has increased, that is 2n minus 1 plus 2, that will be 2n plus 1, then 2n plus 3. So the nth term of the sequence is 2n plus 4 by 2n minus 1 into 2n plus 1 into 2n plus 3. Now for checking convergence of this series, I will apply comparison test, and for that we have to determine a new sequence Vn. Okay, So let Vn equal to 1 by n. 1 by n square, 1 by n square, since this series is also in this form. Now if you calculate this is n, and if you multiply this will be n cube, so n by n cube, that is 1 by n square. So we are taking Vn as 1 by n square. Now I will find the limit n tends to infinity un by Vn, that is limit n tends to infinity. Un is 2n plus 4 by 2n minus 1, 2n plus 1 into 2n plus 3 by Vn, that is 1 by n square. It will be multiplied by n square. So to find the limit, we are dividing by n cube in the numerator and denominator. You know how to find this limit n tends to infinity. I am dividing by n cube in the numerator and denominator. So it will be 2 plus 4 by n and 2 minus 1 by n. I am giving 1 n to each of the factor. So it will be 2 plus 1 by n, and this will be 2 plus 3 by n. So these all will be 0 since n tends to infinity. So the result will be 2 by 2 into 2 into 2, that is 8. So this is 1 by 4. So the limit is a non-zero finite real number. Non-zero finite real number. So according to comparison test, if this limit is non-zero finite real number, then un and Vn converges or diverges together. Okay, so summation un and summation Vn converges or diverges together. So now we will determine that summation Vn is convergent or not. Then we can say about summation of un, the series summation of un. Now summation of Vn, that is summation of 1 by n square. Here you can see that this is a p series where p equal to 2. P series where p is equal to 2. Now by p series, by definition of p series, if p is greater than 1, then the series is convergent. Greater than 1, that is this series is convergent. So hence, by comparison test, since summation of Vn and summation of un converges or diverges together, and since summation of Vn converges, hence summation of un will be convergent. So to check the convergence and convergence of this series, we have applied comparison test. You can apply other test also. So the result is that the given series is convergent. Okay, now I will take another example. The next problem is, okay, so the next problem is 1 by 3 plus 2 by 5 whole square plus 3 by 7 whole cube plus dot dot dot. So I have to check the convergence of this series. Okay, so the given series is like summation of un, where n is equal to 1 to infinite. And what is the nth term? What will be the nth term? Nth term will be the, if you go on like this way, then it will be 1, 2, 3. The nth term will be n by, and the denominator will be 3, 5, 7. The nth term of this series will be 2n plus 1. So, and the power will be 1, 2, 3, 4, like the nth term will be n. So this is the nth term. So you have to determine the nth term if the nth term is not given. In some problem nth term is not given, or in various problems nth term may be given. Okay, now for the checking of convergence of this series, I will apply Cauchy's root test here. Okay, so according to Cauchy's root test, we have to find the limit un whole to the power 1 by n. So here un is n by 2n plus 1 whole to the power n and whole to the power 1 by n. So this will be limit n tends to infinity, n by 2n plus 1, n will be cancelled out. So we are dividing by n in the numerator and denominator. So this will be limit n tends to infinity 1 by 2 plus 1 by n, and since n is tending to infinity, this will be 0 and the result is half. And according to Cauchy's root test, if the limit is a finite real number and it is less than 1, then the series will be convergent. So okay, I have applied Cauchy's root test. Here I should write this Cauchy's root test. So since the limit is non-zero, not non-zero, since the limit is finite real number and it is less than 1, so the given series is convergent. Okay. Okay. So the next problem is test the convergence of the series summation n square minus 1 by n square plus 1 into x to the power n, where x is greater than 0, n equal to 1 to infinity. So we have to check the convergence of this series. So here un equal to n square minus 1 by n square plus 1 x to the power n. Now I will apply D'Alembert ratio test for checking the convergence of this series. So we have to know what is un plus 1, and that will be n plus 1 whole square minus 1 by n plus 1 whole square plus 1 to the into x to the power n plus 1. This is un plus 1. Now we have to find out limit n tends to infinity un plus 1 by un. Okay. Then what will be un plus 1 by un? Un plus 1, that is n plus 1 whole square minus 1 by n plus 1 whole square plus 1 by un, that will be n square plus 1 by n square minus 1, and x to the power n plus 1 by x to the power n. Okay. Now you have to simplify this. So by simplifying, we get n square plus 2n. 1 will be cancelled out, and this will be n square plus 2n plus 2 into n square plus 1 by n square minus 1 into, this will be x. Okay. I forgot to write limit n tends to infinity. Limit n tends to infinity. Now this is equal to limit n tends to infinity. Okay, we are dividing by n square in the n to the power 4 in the numerator and in the denominator. Okay, so this will be I am giving here 1 n square and here 1 n square, so it will be 1 plus 2 by n into 1 plus 1 by n square by 1 plus 2 by n plus 2 by n square into, it will be 1 minus 1 by n square into x. Now since n is tending to infinity, so these all will be 0 and the result is x. Now we know that x is greater than 0. It is given in the question. Okay. Now we do not know the exact value of x. Now according to D'Alembert's ratio test, this is D'Alembert's ratio test. Now according to the statement of D'Alembert's ratio test, if x is less than 1, then the series is convergent. and if x is greater than 1, then the series is divergent. So if x is less than 1, here it is given that x is greater than 0, so combining these two we can write that if 0 less than x less than 1, then the series converges, and if x is greater than 1, then the series diverges. Okay, but if x is equal to 1, if x is equal to 1, then test. What will happen, to see that we have to apply another test. So applying D'Alembert ratio test, we have concluded that if x lies between 0 and 1, the series is convergent, and if x is greater than 1, the series is divergent. Now we will see what happens if x is equal to 1, and for that we will apply Rabb's test. Okay, so I am removing this. Now I will apply. Okay, I have to change the thing. So Rabb's test. So we have to find the limit n tends to infinity n into un by un plus 1 minus 1. Okay, so this is equal to limit n tends to infinity n into un by un plus 1 means n square minus 1 by n square plus 1 into n plus 1 whole square plus 1 by n plus 1 whole square minus 1 into x to the power n by x to the power n plus 1 minus 1. Now we are applying Rabb's test if x is equal to 1, for x equal to 1. So here since x is equal to 1, so this term will not be here because the value of x is 1. Okay, so this will be minus 1, bracket closes. Now limit n tends to infinity, first we simplify this, n square minus 1 by n square plus 1 into n square plus 2n plus 2 by n square plus 2n minus 1. Okay, now limit n tends to infinity, I am multiplying this, that is I am multiplying by n, and that will be n square minus 1 into n square plus 2n plus 2, and denominator is n square plus 1, and here n is common, and that n will be cancelled out with this n. So this will be n plus 2 and this will be minus n. Okay, now I am removing this. Okay, so to find this limit, first we subtract this, so this will be limit n tends to infinity n square plus 1 into n plus 2. Now if we subtract this, the numerator will be minus 4n minus 2. You will simplify it when you solve this sum. I have not shown here the simplification. It will be minus 4n minus 2. So we are dividing by n cube in the numerator and in the denominator. So this will be limit n tends to infinity minus 4 by n square minus 2 by n cube by 1 plus 1 by n square into 1 plus 2 by n. Okay, so here since n is tending to infinity, these both terms will be 0 and denominator will be 1, so the answer is 0, and 0 is less than 1. So according to Rabb's test, we know that if the limit is a finite real number and if it is less than 1, then the series is convergent. Okay, so we see that by Rabb's test the series is convergent. So we get this when we took x is equal to 1. So in the question there was no exact value of x. It is only given that x was greater than 0. So first we applied D'Alembert's ratio test, and from D'Alembert's ratio test we concluded this, and when we took x equal to 1 and we applied Rabb's test, we see that the series is convergent. So the final conclusion, we can write that the given series is convergent if 0 less than x less than 1. It was from D'Alembert's ratio test, and from Rabb's test we see that if x equal to 1, then also the series is convergent. So 0 less than x less than equal to 1, and no, I have told you some wrong. It will be divergent. It will be divergent according to Rabb's test. If the limit is non-finite real number and it is less than 1, then the series will be divergent. Okay, so from the D'Alembert's ratio test we got that the given series is convergent if 0 less than x less than 1, and the series will be divergent if x is greater than equal to 1. X is greater than 1. If x is greater than 1, the series is divergent. We got this from D'Alembert's ratio test. And if x is equal to 1, the series is divergent. We got this from Rabb's test. So combining these two, we can say that the series is divergent if x is greater than equal to 1. Okay. Now I will go to the next problem. So next series, infinite series, is x by 1 into 3 plus x square by 3 into 5 plus x cube by 5 into 7 plus dot dot dot. So this is the infinite series. We have to check the convergence of this series. Okay. Now this given series can be represented as summation of n equal to 1 to infinity un, where un, that is nth term of the sequence, will be x to the power n by 2n minus 1, that is 1, 3, 5. The first terms of the products is 1, 3 in this series, 1, 3, 5 in this sequence. So this will be 2n minus 1, and the second will be 2n plus 1. So this is the given series. So for checking convergence of this series, first we'll apply D'Alembert's ratio test. D'Alembert's ratio test. Okay. So for D'Alembert's ratio test, we need to know what is un plus 1. So first we write un separately. Un equal to x to the power n by 2n minus 1 into 2n plus 1. And then un plus 1 will be x to the power n plus 1 by 2n. It will be n plus 1 in place of n, then 2n plus 2 minus 1, that is 2n plus 1 into, this will be 2n plus 3. Okay, this is un plus 1. Now we have to find the limit n tends to infinity un plus 1 by un. Okay, now we will put the values of un plus 1 and un here. So this will be limit n tends to infinity. Un plus 1 is x to the power n plus 1 by 2n plus 1 into 2n plus 3 by un, that is into 2n minus 1 into 2n plus 1 by x to the power n. So 2n plus 1 will be cancelled out, and it will be x to the power n plus 1 and x to the power n. If we reduce it, then it will be only x to the power 1, and since there is no n, so I can put it out of the limit. So limit n tends to infinity, x into limit n tends to infinity, 2n minus 1 by 2n plus 3. Now I am dividing by n in the numerator as well as in the denominator. So it will be x into limit n tends to infinity, 2 minus 1 by n by 2 plus 3 by n, and since limit is n is tending to infinity, so this will be 0 and the limit will be equal to x. Okay. Now we do not know the value of x, exact value of x. So according to the statement of D'Alenberg's ratio test, we can say that if the limit is a finite real number, and since x is a finite real number, and if the real number that limit is less than 1, then the series is convergent. That is, if x is less than 1, then convergent, and if x is greater than 1, then divergent, and if x equal to 1, then the test fails. So what will happen if x equal to 1? To check that, we have to apply another test. Okay, so now for x equal to 1, I will apply comparison test. Okay, so now I will check for what will be the result of convergence or divergence of this series if x equal to 1. So if x equal to 1. Okay, so I am applying comparison test. So comparison test, first I am writing un is x to the power n by 2n minus 1 by 2n into 2n plus 1, but here we are checking for x equal to 1, so un will be 1 by 2n minus 1 by 2n plus 1. Now we are assuming that vn equal to, we are taking vn as 1 by n square. Okay, now we'll find the limit n tends to infinity un by vn. So this will be limit n tends to infinity, un is 1 by 2n minus 1 into 2n plus 1 by vn, that will be into n square. Okay, now this will be equal to limit n tends to infinity. So I am dividing by n square in the numerator as well as in the denominator. So it will be 1 by 2 minus 1 by n into 2 plus 1 by n. Now the limit will be, since n is tending to infinity, this 2 will be 0. So the limit will be 1 by 4, which is a non-zero finite real number. So you know that according to the comparison test, if the limit is a non-zero finite real number, then un and vn, summation un and summation vn, these two series converges or diverges together. Okay, now to know the convergence of summation un, we have to check the convergence of summation vn. If we can find that summation of vn is convergent or divergent, then by comparison test we can say that summation un will converge or diverge. Okay, now we have to check for summation vn. Now what is summation vn? Summation of 1 by n square. Now okay, I am deleting this. So summation of vn of Vn is summation of 1 by n square. Now this series is in the form of a P series, okay, where this is a P series where P is equal to 2. Now we know that in a P series, if the value of P is greater than 1, then the series will converge. Okay, so since P is greater than 1, then summation of Vn is convergent. Now since summation of Vn is convergent, now according to the comparison test, we can say that summation of Un is also convergent. So for x equal to 1, we saw that summation of Un is convergent by comparison test, and by applying D'Alembert's ratio test, we have already concluded that the series is convergent for x less than 1 and divergent for x greater than 1. Now the final conclusion is then summation Un is convergent for, it was convergent for x less than 1 by D'Alembert's ratio test, and just we saw that it is convergent for x equal to 1 by comparison test. So summation Un is convergent for x less than equal to 1, and summation of Un is divergent for x greater than 1, which I got from the D'Alembert's ratio test. So this was the solution of the given series. So I have in this video I have shown you some examples of infinite series and how to check the convergence of those series. So you have to solve these type of problems. Okay, then it will be easy to understand the methods and the tests how to check the convergence and divergence of a given series, infinite series. Now this was all for this video. If you face any problem during when you are solving this type of problems, you can contact with me. My contact details is given at the first of this slide. Thank you.